In this video, we'll be covering the topology of general relativity. Now, let's talk about manifolds. In other videos, we've gone into more depth discussing various examples of manifolds, but in this video, I'm going to talk about one of the most important cases that's the very foundation of modern physics, space-time. So, to get a better understanding of how space-time works, I think it's best if we look at the more familiar, but not too unrelated idea of magnetic fields. Magnetic fields are commonly imagined as these curvy lines that come out of magnetic poles. You probably even had a class where you've used iron filings on a piece of paper to see the magnetic field lines. A common misconception is that these lines form locally around magnetic objects. Well, this isn't the case. The magnetic field can be imagined as a massive grid, or a manifold, that is spread across the universe, leaving no corner uninhabited. It's only when in the presence of a magnetic object that the field interacts and distorts, ultimately manifesting as a magnetic force represented by the curved field lines. Space-time is much like this. Just like magnetic fields, there is a very large manifold stretched across the universe, that of space and time itself. The manifold does not interact with magnetic objects, however. The manifold actually interacts with any objects. Well, any objects that have mass. So how do these distortions manifest? They appear as the force of gravity. And this idea was first covered in Albert Einstein's theory of general relativity. We can see here in the simulation that the more mass the object has, the more severe the space-time distortions are, which makes sense because that means that the more mass correlates to a stronger gravitational force, which we know to be true. Now, we're starting to venture into topology-esque territory, and this becomes even more apparent with the introduction of geodesics. Geodesics refers to finding the shortest pathway on a curved surface. As we have now established, the shape of space is a lot more curved than we initially realised, and that things tend to move through space, so it's not unreasonable to conclude that geodesics may be somewhat relevant. The movement can be neatly described by the geodesic equation. In the equation, the term s here refers to the specific scalar depending on the scenario. For us, we're talking about general relativity, so we can substitute this in for time. By using the chain rule, we get this new equation. To go through what each variable means is frankly beyond the scope of this short video, but what is important is its use. By using this equation, we can model and compare the differences between Einstein's theory on gravity and Newtonian gravity. However, the geodesics only form half of the solution. We still need to use this in combination with Einstein's field equations to get the full picture. It may look simple, but Einstein's field equations quickly become a steep drop-off into complexity. Each of these terms refer to a tensor, the Einstein tensor, the metric tensor, and the stress energy tensor, along with a cosmological constant. A tensor can be thought of similar to a vector field. In fact, vectors are just kind of a tensor, a first rank to be precise. But similar to having a magnitude and one dimension, a tensor can have an nth dimension. So, for Einstein's field equations, we have three different tensors, effectively meaning an entirely different set of data describing most of the physical properties of an object, how they change, and how they interact, making this short equation a nightmare to do anything with. However, there are some ways around this, and this comes in the form of our last link for space-time and topology. Einstein-Gauss-Bonnet gravity. This part has to be pretty comprehensive, as any detail requires a whole nother rabbit hole to go down. With the massive success of Einstein's theory of general relativity, many other accomplished physicists and mathematicians began to revise the fundamentals, providing their own alternatives. Einstein-Gauss-Bonnet gravity is one such case. First proposed by Lanczos and formalised by Lovelock, Einstein-Gauss-Bonnet gravity stands out from the others. This is because it is one of the few theories that requires no extra tensors to be considered other than the ones in general relativity, while also providing methods of solution that prevent Ostrogradsky instability. Okay, I know that was a lot of big words, so I'll break it down to be a bit simpler. This theory is really important as it doesn't need any special additions to Einstein's original work, and when the equation is used, there are no possibilities that you may get a false answer, or more interestingly referred to as explosive vacuum decay. You might have noticed the use of the phrase Gauss-Bonnet. This should sound familiar, as Gauss-Bonnet theorem was covered in our presentation Investigating Topology, Vector Fields and the Gauss-Bonnet Theorem. So yet another link to topology. If we recap Gauss-Bonnet, we know that the theorem can be used to find the Euler's characteristic of any given shape. When we apply this to space-time, the Gauss-Bonnet theorem can be used to quantify the shape of space-time manifold, and used to produce an entirely different set of field equations from that of the Einstein's field equations. This in turn allows us for an alternative path to solve Einstein's field equations